Continuing with the same data, we are now going to calculate the standard deviation using the computational formula. While it may look more confusing, most of the time it's the easier formula to use because there are less computations to do. This is the formula a computer or calculator would use to calculate the standard deviation. There are two key numbers we need to plug into this formula. Those are the sum of x's and the sum of x squareds. So in my table, I only need two columns of information to use this version of the formula. The leftmost column, again, are my data values, which I call x, and the second column is going to be my x squared values. I calculated those simply by squaring the numbers from the leftmost column. Those calculations are shown in red. I need to take the sum of both these columns. The second column sum gives me the sum of x squared, which for tire brand number 1 is 4,550. I plug in that value for the sigma x squared symbol in the formula on the left side of the numerator. From that value, I need to subtract the sum of x's squared divided by n. Here you can see the sum of x's. That is a value I need to square and then also divide by n. I know it can seem confusing, but the sum of x squared values is not the same as the sum of x values, which is a number I'm going to square. The 4,550 came from squaring all the x values first and then adding them up. The right side of the numerator tells me to add all the x values up first, which can be 150, and then to square that 150. I would then again divide by n, which in this case is 5, because I have 5 data values just like before. When I do 150 squared divided by 5, I should get 4,500. And subtracting 4,500 from 4,550, that will give me a numerator of 50, which is exactly what the numerator was in the defining formula calculation. So taking the square root of 50 divided by 4 gives me the exact same value for the standard deviation as the defining formula, which is 3.54. I recommend pausing the video and/or taking a closer look at the calculations by viewing the PDF version of this slideshow. You can find that file in the Week 3 file folder on Moodle. The two formulas we used for that example were to calculate the standard deviation of a sample. We used the variable s to represent sample standard deviation. If the data we were analyzing was population data, the calculation would be slightly different, but very similar. Here on the screen are two formulas for calculating the standard deviation of population data. You can see many of the symbols have changed. Instead of x bar, we are now using mu to represent the mean of the population. And instead of using s, we are now using a lowercase sigma to represent the standard deviation of a population. While the formulas look very different, there's actually only one minor change, and that is, instead of the denominator being n minus 1, we instead divide by just n. I use the capital N because a lowercase n represents sample size, and a capital N represents population size. If the data we had for the tires was population data instead of sample data, I wouldn't have to do all my calculations over again, because the numerator for each formula would be the same. Instead, all I would do different is divide by 5 instead of dividing by 5 minus 1. This actually makes more sense than dividing by n minus 1 anyway, because the standard deviation is basically an average of how far off my data is from the mean. In the sample standard deviation formula, I divide by n minus 1 so that my result is a little bit higher. This is because the sample standard deviation is supposed to be an estimate of the actual standard deviation of the population. When I take a sample, I usually don't get the extreme values that a population dataset would have. Those are sometimes called outliers. So I try to make my sample standard deviation calculation a little bit higher to account for those extreme values of a population I might not have in my sample. As I mentioned before, the first thing we can use standard deviations for is to compare the variability of different sets of data. For the two tire brands, we compared the standard deviations directly, determining that tire brand number 2 had more variability because the standard deviation was higher. However, it is not always appropriate to compare standard deviations directly. We also have to take into account the mean of the data. Taking a look at the example on this slide, I want you to think about for a minute what a dataset might look like if it has a mean of 20 versus what a dataset might look like if it had a mean of 200. Obviously, the second dataset with a mean of 200 should have much larger numbers in it. Now, if both those datasets had the same standard deviation, let's say 5, you might think the variability is about the same, but that wouldn't be fair to say. It would be more fair to compare what's called the coefficient of variation, which is a ratio of the standard deviation compared to the mean. We would say that for dataset 1, the variability relative to the mean is much higher. It's 25% for dataset number 1 versus 2.5% for dataset number 2. I calculated those by taking the standard deviation and dividing by the mean, and then I multiplied by 100 to turn it into a percentage. I want you to think about two different people, and think about if one person had $1 million and another person had $100. Then let's say they both lose $10. On one hand, you could say they lost the same amount of money. They both lost $10. But on the other hand, you could say that the $10 didn't mean as much to the person who had $1 million to start when you compare them to the person that had only $100 to start. There is less variability for the millionaire, relatively speaking. The coefficient of variation takes that into account. Having a standard deviation of 5 in dataset 1 means there is a lot more variability relative to the size of the data when comparing to dataset number 2.